Hello guys, welcome back to my channel Gamma Die Gamma. So in this video, I would like to do some more linear algebra, and I would like to do a topic that I think most people don't understand pretty well, as change of bases. So let's get started. Okay, so before talking about change of bases, let's understand what bases are. So I'm sure you guys have some physics background. If not, even some coordinate geometry background is fine. So understand that whenever we talked about stuff, and we talked about properly structuring and mapping stuff, we had our axes. Is the x-axis, the y-axis, and for most of your time in middle school, I'm sure you enjoyed graphing stuff like this on the x and y-axis. But then when you grew up and did some three-dimensional geometry, you also started to consider the z-axis, and objects, at least in our experience, are in 3 dimensions. Again, let's not go to talk about higher dimensions. There are higher dimensions, obviously, but okay. I talk about dimensions, and you have some experience with the word empirically, but this has a pretty formal mathematical definitions too that's associated with bases. Anyways, so the essence of bases, this is the standard basis that we work with. These axes are mutually perpendicular. Okay, so the basic idea of bases is that any point in this space that is basically what should I say? I'm trying to make it more easier for you to understand, and I'm losing some mathematical rigor in that. But the space that is basically, I want to say spanned, but I haven't explained what span is. So any point in this space over here can be written as some combination of this y direction. The y direction we usually call j cap, the x direction we call I cap, and the z direction we call k cap. These are unit vectors. The basic principle of, or reason for denoting them as unit vectors is they have magnitude 1. So you can just, because if you have a point like this over here which has x0 and z0, so 0 comma, I don't know, 5 comma 0, you can denote this point, let's call it P, to be 0 I cap plus 5 j cap plus 0 k cap. That's to say that this point has 0 x's or 0 I cap directions in it, 5 j cap directions in it, and 0 k cap directions in it. But if we want to denote an arbitrary point, see somewhere over here, I don't know, just 1, 5, let's make it -3, 5, and 4. Okay, this point, let's call it Q. So now Q can be represented as -3 I cap plus 5 j cap plus 4 k cap. So that's to say that this point Q can be basically broken down, and I'm going to emphasize on this, broken down into 3 parts, based on these bases that we have, at least for this space. And the space that I was trying to say that these bases spanned was R3, but this is it's a little technical for, because I haven't made a video on spanning and like vector spaces yet, so it's like an offshoot, but please bear with me. So yeah, so this Q can be basically broken down into like three simple parts, like what combination of the I cap direction or the X direction make up Q, what combination, and again I'm stressing on combination of what combination of the J cap direction or the Q direction make up Q, and what combination of basically the Z direction, the K cap direction, make up Q. I mean, instead of using these standard bases, and I can like denote these bases as like vectors. So I cap is the vector 1 0 0, J cap is 0 1 0, and K cap is basically 0 0 1. Instead of using these, we can use any other three vectors, but the condition is they should provide like distinct information. So like J cap provides information that I cap cannot, like I cap has no J cap or K cap directions in it. So any point that is denoted as just I cap will only be along this line. Similar thing with J cap, like any point denoted with just J caps will be along this line. Fine, but if we take like a combination of them, say arbitrary A, constant A, I cap plus arbitrary constant B, J cap, then the set of all these points will be in this plane, because then you'll be adding the I cap, J cap, I cap, J cap, for whatever values, this plane. I mean, this will go back to the negative I cap, J caps too. So this set of points that you can denote is basically the span. That's the span. That's what I've been stressing so far. And similarly, then we just had two. Then if you add like a K cap to the mix, make this point say C K cap, then we originally had a plane for like two directions, I cap and J cap, but with K cap we also have a higher direction and a lower direction. So this will basically cover all of three-dimensional space, and that's R3. That's why we need like distinct information. Like J cap was providing information that I cap could not. Similar thing, K cap was providing information that J cap could not. That's why this idea of providing new information is what is called independence of vectors. In this case, basis vectors, because they form a basis. That's why, I mean, if you had, instead of say J cap, say you had J squiggle, for example, and this was say 2 0 0, and you wanted to construct a basis with I cap as always, J squiggle, and K cap as always, you wouldn't be able to, because J squiggle is a multiple, or is a combination, is a linear combination of I cap. I mean, you take two I caps, you get J squiggle. So J squiggle is actually like in the same direction as I cap. So, and then if you like basically like take a combination of them, if you check the space that these guys span, I mean, I cap is here, J squiggle is here, and K cap is up there. So it'll just be this. You won't get this direction because there is no like new information there. That's why that's this new information idea is called independence. Like the three vectors should be linearly independent. Otherwise, if they're like parallel, or like if you had like say I cap and J cap and like K cap to be like a sum of both of them, or any like linear combination. And when I say K squiggle was like A squiggle I cap plus B squiggle J cap, even then it wouldn't work, because then K squiggle would be in the span of I cap and J cap. So again, that it would be like in this plane, and it wouldn't provide the extra information of a higher dimension or higher quantity. So I think of bases as basically scaffoldings of whatever space they are spanning. So whatever space they are spanning. In this case, we extensively talked about R3 because that was the space they were spanning, and the dimension I've been emphasizing was actually, the idea of dimension was actually the number of basis vectors you use to basically span a space, span a given space. In this case, the dimension was 3 because we had 3 vectors, 3 basis vectors. So you can have like 4 basis vectors in like a spanning R4 or something. But if they have to be, if they are going to be basis vectors, they have to be independent. Like you can't like have a redundancy of information. Like here, like with the J squiggle case, we were having like a redundancy because it was in the same direction as I cap. So that won't span. Like if you have 4 vectors and they're not independent, if there's some redundancy, then they won't exactly form span R4. They'll form they'll span a lower space, a lower dimensional space. So like in this case, when J squiggle was pointing in the same direction as I squiggle, we were getting a 2-dimensional span. We were getting like this plane that they were spanning in. A plane is basically 2-dimensional. The span had dimension 2, not 3 in the original JCap case. So I know this was pretty long for an introduction, but I hope you get an idea. I mean, since I didn't give a proper introduction to vector spaces, it's just an offshoot. Okay, so we talked about bases and the standard way of that we did stuff, having these coordinate axes over here. At any point, I don't know, call it W vector, could be denoted as some, I don't know, S1 I cap plus S2 J cap plus S3 K cap, where I can write I cap as say 1 0, column vectors 1 0 0 and 0 1 0 and 0 0 1. Okay, fair enough. Now this is like W expressed in the standard basis that I'm going to denote as E was like this. And if you know some linear algebra already, you can like already write this as a matrix of 1 0 0 0 1 0 0 0 1 multiplied with S1 S2 and S3, and if you do the multiplication, it will turn out to be exactly, because this is the identity, it will turn out to be exactly S1 S2 and S3. Okay, now I want to express W in like a new basis V. I'm going to call it say A for now. Then for if we have a new basis, we need basis vectors, right, to have linear combinations of them to denote anything in that space. So assume like our vectors are say v1 v2 till vn. Say this is an n-dimensional space, so we're working officially in Rn. So we want to express W in a basis V. We need to take linear combinations of this, like we had like S1 S2 S3 were like arbitrary coefficients, and 1 0 0 0 1 0 0 0 1 were the specific vectors. So arbitrary coefficient I'm going to denote as A1, A sub 1, and then our first vector V1 plus A sub 2 V2, and then we keep doing that until A sub n Vn. And I mean I can write this as like a column vector like this, It's probably a slightly cooler way of doing it. An Vn. And again, as I did for this example, I can do the same, except I'll have a matrix with like v1, v2 till vn on the columns, multiplied with a1, a2 till basically an. And now the catch here is that here, earlier we had the identity times a vector, so we got the vector itself. Here we won't have that, because v1, v2, v3 aren't exactly standard. This is like an arbitrary coordinate system or arbitrary basis. And this matrix we call the transformation matrix. But now notice that this guy a1, a2 till an is actually a point that is denoted in this new basis. So this guy is actually like some point in this like new crazy n-dimensional basis system. So it's actually this guy, that's W expressed in a different basis. So then this T is actually the transformation matrix from basis V to basis E. Because if you apply that on a vector expressed in basis V, it gives you a vector W. I did a mistake here. I wanted to say that we try to start expressing W as like a linear combination of other vectors. And since W is like S1, S2, S3, it's in the standard basis. So these coefficients that the column matrix that these coefficients form are actually a point in this new, written in terms of these new bases. And if you apply this matrix on it with the matrix which has the basis vectors on the columns to this point, it transforms you from V to E, because that's what we set our equation equal to originally, the W expressed in the standard basis. I hope I'm clear on this part. Okay, so previously we learned how to change the basis for vectors. Let's change the basis for matrices now. Okay, so say we have some matrix boldface S, and every matrix is a change of basis for a vector. I mean, we just learned that. I mean, we had a T, so all the columns of a matrix will basically be the new basis vectors. So take a matrix S that is basically a transformation or change of basis from E to S, where if you put that on a vector, and I make that act on vector W in the standard basis, and the result is another vector B, but which is now in basis S because we applied this change of basis matrix S. Now instead of like W expressed in the standard basis, let's take W expressed in basis V and basically try to replicate the process. But instead now, because W is not exactly, W in basis V isn't identically equal to W in basis E, this will be a different matrix, say boldface S dash, which will take stuff from V and put it, now this is a little complicated, in S of V. So we'll have a new vector, say I don't know, B dash, but in S of V after you apply this S dash on W in space of V. Now you might ask, why isn't this going from V to S like the top case? That's because if this went from V to S, then I mean there would be a slight problem. Then this wouldn't exactly replicate this process, because we're working in basis V, so the input is V, and then we end up at a basis S. Now a basis defined with respect to what? That is actually the main question. Like, basis defined with respect to what? I mean, you can say that stuff is defined with respect to bases, but in this case, if we want to look at the picture of bases as basically columns of a matrix, then this question should come up. Bases with respect to what? I mean, these column vectors are expressed in what basis? You know, that question should come up. So I mean, in this case, assuming say S can be expressed as a bunch of like vectors, I don't know, A, B, C, whatever, D, E, F, whatever, G, H, I, whatever, basically goes on. So then this S dash is actually some other numbers in the columns, but since we're working in basis V originally, we're purely in basis V. Otherwise we won't be able to replicate this process. Since we're purely in basis V, this instead of like having ABC, we have ABC but expressed in basis V. Same thing with DEF, because all these are vectors, right? We can express vectors in terms of on another basis that we saw on the previous page. GHI but in basis V. We keep doing that. Now we learned if you want to express something in a different basis, like how do we relate like something that's expressed in basis V or arbitrary basis to something that's expressed in a standard basis? Well, what do you do? Is basically multiply both sides by a change of basis from V to E, like or original change of base matrix T from the previous page. And when I do that, I will have whatever T is multiplied with ABC in basis V, DEF in basis V, GHI in basis V. And when I do that, when I basically try multiplying everything, this will act on individual columns. You can check that, doing some like basic examples. And we will basically get ABC but in basis, the standard basis now. Multiplying like two matrices together is basically like multiplying each column of the second matrix by matrix individually. That's the idea. And this is precisely our S. So if you apply a change of basis, like transformation matrix T on our boldface S dash, which was taking stuff from V to S of V, you get boldface S, which takes stuff from the standard basis to S. So basically T is changing this inside this inner S of V, like this inner V to E on transformation. You can think about it that way. But now here's the problem. Like, think about it this way: if these are like functions, the left hand side is taking input v, so call this f. It's taking an input from space v, basis v, and giving out something that's in E. And think about the left hand side this way. Say this is a function g, that takes input in E, spits out stuff in S. There is like, how can we set equalities when like the domain and codomain of functions aren't matching? So in order to basically tune stuff down, our S from E to S, T from V to E, S dash from V to S of V. Okay. But now, we make them act on something. Say, in this case, we want something in E. We can take W, which is already in E. We want something in V, so we take W expressed in basis V. Now we know from the previous page that W in basis E is the transformation matrix from V to E acting on W expressed in basis V. So W expressed in basis V can be written as inverse, the T inverse. Now T goes from V to E, inverse will go from E to V. It's just the same process but like reversed, acting on W of E. So I can just make that substitution. Instead of W in basis V, I can have T inverse, which will take stuff from E to V, acting on W of E. Now the advantage of this is, now look, we have the same input over here, E, on both sides. So just ignore this like test vector W of E we took. We're interested in the matrices now. So boldface S from E to S is equal to T from V to E of S, boldface S dash of V to S of V times T inverse E to S. So the S, boldface S dash that we were trying to find is actually T inverse from E to V, S of E to S, and T from V to E. That's actually the formula for our boldface S dash over here. So I mean, the important things we learned, at least for now, is that any vector expressed in standard basis is the transformation matrix times the vector expressed in the new basis. And this transformation matrix has the basis vectors as its columns. That's why the transformation matrix for a standard basis is the identity, because it just makes sense, right? I mean, 1 0 0 0 1 0 0 0 1 are the basis vectors for the standard basis, at least. Now a fresher perspective I offer to the formula on the for change of basis of matrices is, say you have B, like a vector in expressed in some basis S. You get that after applying boldface S, that will take vector in vector as which is expressed in standard basis to vector expressed in basis S. It will take an input W, which is expressed in E. And again, as I said, we want to replicate this process to get B dash expressed in S of V, like S but expressed in terms of basis V. We have a new matrix that will take from V to S of V, a capital boldface S dash, This will have W expressed in V as its input. Now, well, looking at these guys, I mean, instead of just S, we can S in terms of standard basis. There was no need to write this, but it will make stuff clearer. I mean, what's the connection between this B dash vector and this B vector? Well, the B dash vector, which is in space S of V, is nothing but the transformation matrix from V to V. I meant to say, so let's do this again. B in S of E is actually nothing but the transformation matrix applied, which takes from basis V to E on this B dash vector, which is in S of V. Again, like the previous case, it's like the inner like the off, inside the bracket part is changed by this transformation matrix. Think about it that way. Okay, fine. We can use this now, because now we can write B vector as boldface S from E to S, W sub E is equal to transformation matrix from V to E, and then boldface S dash from V to S of V, which is acting on W sub V. Now again, there's a domain codomain problem over here. So we remember that W in the standard basis is the transformation matrix from V to E of the W in the new basis V. So we basically use that over here, because the W in basis V will just be inverse from E to V of W of E. So I'm just going to use that. T from V to E, boldface S dash from V to S of V, and T inverse, which will take stuff from E to V, acting on W of E. Again, now ignore the input vectors like we usually do in quantum mechanics, and we're playing with operators. We get the same formula again. So I mean, this was another perspective of looking at it, because instead of like looking at the columns of a matrix expressed in a different basis, probably easier to think about vectors and then transforming vectors. Okay. Now the applications of this are particularly important when we're trying to find the eigenvalues and eigenvectors, and I'm going to make a separate video on this, like a grand video on this, because it's so important in quantum mech and like in many other branches. I think Google's search algorithm relies on a theorem. Google's algorithm of ranking pages relies on a theorem in eigenvalues, eigenvectors, called the Perron-Frobenius theorem. Now that's a complicated discussion, but eigenvalue, eigenvectors is the process of basically writing a matrix, any matrix, in terms of some matrix, a diagonal matrix, and the inverse of the first matrix. And this is useful because if you're calculating higher powers of this guy, for example, notice the P inverse and the P will cancel to an identity, and we just have P, and since this is diagonal, like raising a diagonal matrix to any power is just squaring the individual entries of that. So that's why this is so useful. If you can express any matrix in terms of this form, you can like raise it to any infinite power or anything you can do. So as I say, this sort of decouples the system, makes stuff easier to solve. It's like a more convenient way of looking at things, like an easier way. Like you can look at stuff from like a hard perspective, like from a top, but like if you look at it from a comfortable point of view, you get a bigger picture. It's like that. That's why this was particularly useful, because this if you notice, this PDP inverse is actually the expressing a matrix A in the basis, in terms of the, you know, expressing A in the basis of its eigenvectors, like in an eigenbasis. So this matrix P has all the eigenvectors on its like diagonal, basically. On its columns, basically. That's why this topic of change of basis was useful, and I hope you got a little more insight than you usually would. Thanks for watching. Now I know this video has already been like the longest one in the most recent times, but I would urge you to like, share, and subscribe to my channel, guys. Recommend it to your friends. Spread the word of Gamma Di Gamma in the math community. And in the meantime, stay home, stay safe, keep doing math, and peace out.